Let's talk about something that could change the way you see data forever. How do we catch those sneaky outliers before they cause chaos? PCA-based anomaly detection is the secret weapon. Principal component analysis isn't just math magic, it's the ultimate decluttering tool for your data, stripping away noise while keeping the most important bits. But how does that help spot anomalies? That's exactly what we're diving into. First, we'll break down PCA, making sense of eigenvalues and eigenvectors without the headache. Then, we'll walk through the step-by-step process, standardizing data, computing covariance matrices, and projecting onto principal components. Once we have that foundation, it's time to catch anomalies using different distance metrics like Euclidean and Mahalanobis, and we'll explore the different types: point anomalies, contextual, collective, and even temporal. Next, we'll go hands-on with a complete workflow from pre-processing data to scoring anomalies and interpreting results. But of course, nothing is perfect. PCA has its own challenges: outliers, nonlinearity, and the struggle of picking the right number of components. We'll compare PCA to other anomaly detection methods like isolation forest, and then jump into real-world case studies in finance, cybersecurity, and healthcare. Finally, we'll evaluate how well PCA actually works using precision, recall, and Rocky curves before looking at the future: deep learning, real-time detection, and explainable AI. Stick around, because by the end, you'll see just how powerful PCA is in spotting anomalies before they become disasters. Anomalies in data can be subtle, deceptive, and often go unnoticed until it's too late. Whether it's financial fraud, cybersecurity threats, or medical irregularities, spotting these outliers early can make all the difference. But with massive data sets and countless variables, traditional methods struggle to keep up. That's where principal component analysis, PCA, steps in. PCA is more than just a statistical technique. It's a way to cut through the noise, reduce complexity, and bring hidden patterns to the surface. By transforming high-dimensional data into a more manageable form, PCA helps us focus on what really matters while filtering out irrelevant variations. This ability makes it a powerful tool for anomaly detection, allowing us to identify unusual behavior in datasets with precision and efficiency. But why should you care? Because anomalies aren't just numbers, they represent real-world issues. A fraudulent credit card transaction, a security breach in a network, or an undiagnosed health condition, all of these can be detected earlier with the right approach. And in a world overflowing with data, being able to separate meaningful anomalies from random noise is a critical skill. In this session, we'll uncover how PCA works, why it's a game changer for anomaly detection, and how it's applied in industries like finance, cybersecurity, and healthcare. We'll break down the core mathematical principles, guide you through the PCA workflow, explore real-world case studies, and discuss its strengths, limitations, and future potential. So if you've ever struggled with high-dimensional data, dealt with misleading outliers, or wanted to improve anomaly detection in your field, this is for you. By the end of this, you won't just understand PCA, you'll see anomalies in a whole new light. Let's dive in. Before we dive into how PCA helps with anomaly detection, let's first break down what principal component analysis, PCA, actually is. At its core, PCA is a dimensionality reduction technique, meaning it takes high-dimensional data, full of overlapping and redundant information, and compresses it into a lower dimensional form while preserving as much important variance as possible. In simpler terms, PCA helps us keep the meaningful patterns while getting rid of the clutter. Imagine you're looking at a complex data set with dozens or even hundreds of variables. Some of these variables might be strongly correlated, meaning they're just repeating the same information in different ways. Instead of analyzing them separately, PCA finds the most important directions, principal components in which the data varies the most, and reorients the data set along these axes. This not only makes the data easier to visualize, but also more computationally efficient for tasks like machine learning and anomaly detection. PCA works by computing eigenvalues and eigenvectors of the covariance matrix of your dataset. Sounds complicated? Don't worry. We'll break it down step by step. The eigenvectors represent the principal components which define new axes capturing the most variance in the data. The eigenvalues, on the other hand, tell us how much variance each principal component holds. By selecting only the top principal components, we can reduce the data's dimensions while retaining most of its meaningful structure. But why does this matter for anomaly detection? Because anomalies tend to stand out when data is projected onto its principal components. Instead of being hidden in a complex high-dimensional space, outliers become more detectable when viewed through a reduced dimensional lens. This is why PCA is so widely used in fraud detection, network security, and even healthcare diagnostics. In the next section, we'll break down the exact steps to compute PCA, from standardizing data to computing covariance matrices, performing eigenvalue decomposition, and finally projecting data onto principal components. By the end of this, you'll not only understand PCA, you'll see how it transforms data into something much more insightful and powerful for anomaly detection. Let's keep going. Now that we understand what PCA does, let's break down exactly how it works step by step. While PCA might seem mathematically heavy, the actual process follows a logical sequence. By the end of this, you'll see how raw data transforms into a cleaner, more insightful representation where anomalies become easier to detect. Before doing anything, the dataset needs to be standardized to ensure that all features contribute equally. PCA is sensitive to differences in magnitude, so without standardization, variables with larger scales would dominate the analysis. This is done by subtracting the mean from each feature and dividing by the standard deviation, resulting in a dataset where each feature has a mean of 0 and a standard deviation of 1. Once the data is standardized, the next step is to compute the covariance matrix, which measures how different features vary together. If two features have a high covariance, they contain similar information, meaning some of their details might be redundant. The goal of PCA is to reorient the dataset in a way that captures the most variance while reducing this redundancy. With the covariance matrix in place, the next step is performing eigenvalue decomposition. This involves extracting eigenvalues and eigenvectors from the covariance matrix. Eigenvectors represent the new axes or principal components along which the data is spread out the most. Eigenvalues indicate how much variance each principal component captures. The principal components are ranked by their eigenvalues, meaning the first principal component accounts for the most variance, the second captures the second most, and so on. Now comes the decision of how many principal components to keep. Keeping all components defeats the purpose, and keeping too few might mean losing valuable information. The trick is to select enough components to capture most of the variance while ignoring insignificant ones. A common rule of thumb is to retain the first k components that explain at least 95% of the variance. This is often determined using a scree plot, which visualizes the eigenvalues and helps pinpoint the optimal number of components. Once the principal components are selected, the final step is to project the original data onto this new lower dimensional space. This is done by multiplying the standardized data by the selected eigenvectors. The result is a transformed dataset with fewer dimensions, capturing the most essential patterns while filtering out noise. By reducing the data to its most informative dimensions, PCA makes it easier to spot anomalies, those data points that don't fit the general structure. Since normal data aligns well with principal components, anomalies tend to deviate significantly, making them easier to detect using distance-based metrics. Now that the data is transformed, the next step is understanding how different distance metrics help in measuring anomalies in PCA-transformed data. Let's move forward. Now that PCA has transformed our data into a lower dimensional space, the next challenge is identifying which data points are anomalies. But how do we actually measure what's normal and what's suspicious. That's where distance metrics come in. These mathematical tools help us quantify how far a data point deviates from the expected pattern. The farther a point is from the normal cluster, the more likely it is to be an anomaly. But not all distance measures work the same way, and choosing the right one can make all the difference in accuracy. One of the most commonly used metrics is Euclidean distance, which simply measures the straight line distance between 2 points in space. It's intuitive, easy to compute, and works well in low-dimensional spaces. However, it has limitations, especially in high-dimensional data where distances become less meaningful due to the curse of dimensionality. Another issue with Euclidean distance is that it treats all features equally, which might not always be ideal when some variables have more influence than others. To address some of these limitations, we can use Manhattan distance, which measures the path along grid-like steps rather than a direct straight line. This metric is particularly useful when dealing with sparse data or when different features contribute differently to anomalies. It's also less sensitive to outliers compared to Euclidean distance, making it a solid alternative in many cases. For more sophisticated anomaly detection, Mahalanobis distance is often a better choice. Unlike Euclidean and Manhattan distances, Mahalanobis distance takes into account the correlations between variables by incorporating the covariance matrix. This means it adjusts for differences in scale and can better detect anomalies in data sets where different features have different variances. It essentially tells us how many standard deviations a point is from the mean in a multivariate space, making it highly effective in spotting anomalies that wouldn't necessarily stand out in simpler distance measures. Each of these distance metrics has its strengths and weaknesses, and the best one depends on the structure of the data. Euclidean is simple and works well in small, well-scaled datasets. Manhattan is useful for high-dimensional spaces with independent features, and Mahalanobis is powerful for complex, correlated datasets. In anomaly detection, distance metrics help us define thresholds. Any point beyond a certain distance from the normal cluster can be flagged as an anomaly. Now that we have a way to measure how unusual a data point is, it's time to explore the different types of anomalies, because not all outliers behave the same way. Some are easy to spot, while others are only detectable in specific contexts. Let's break them down. Not all anomalies are created equal. Some are obvious, like a sudden spike in fraudulent transactions, while others are sneaky, hiding in patterns that only become suspicious in certain contexts. To truly understand anomaly detection, we need to break down the different types of anomalies, because what looks normal in one situation might be a red flag in another. The most straightforward anomalies are point anomalies, single data points that stand out dramatically from the rest of the dataset. Imagine temperature readings in a climate monitoring system. If most values hover around 20 PE but suddenly one jumps to 100, that's a clear outlier. These are the easiest anomalies to detect and are often the first ones flagged by standard anomaly detection methods. Then we have contextual anomalies, which are only unusual under specific circumstances. Take electricity usage, for example. A sharp increase in power consumption might be normal in winter, but could signal an issue in the summer. Context matters, and these anomalies require additional information, like time, location, or category, to be correctly classified. Next up are collective anomalies, where a group of data points collectively form an abnormal pattern, even if individual points don't look unusual on their own. A classic example is a series of rapid transactions on a credit card. Each transaction might be within a normal spending range, but together they indicate potential fraud. There are also temporal anomalies, where data patterns change over time in unexpected ways. Imagine website traffic suddenly dropping by 80% overnight with no explanation. If it's due to a holiday, it's fine. If it's because of a system failure, it's a serious problem. And then there's one anomaly most users don't like: false positives. Ever had your credit card blocked because the system thought your legitimate purchase was fraud, or received an alert that turned out to be nothing? False positives are anomalies that aren't actually anomalies, and they can be a major pain. In anomaly detection, we always aim to strike a balance, catching real threats while minimizing false alarms. Now that we understand the different types of anomalies, the next step is figuring out how to systematically detect them using PCA. We'll go through the full workflow: data pre-processing, dimensionality reduction, and scoring anomalies to see how this all comes together in action. Let's get into it. Now that we understand the different types of anomalies, let's put everything together and walk through the step-by-step process of detecting anomalies using PCA. This workflow is crucial because anomaly detection isn't just about running a model, it's about preparing the data properly, reducing its complexity, and applying the right methods to identify unusual patterns. A well-structured workflow ensures that anomalies aren't just detected, but also correctly interpreted and acted upon. The first step in the process is data pre-processing. Raw data is rarely clean and ready to use. It may contain missing values, inconsistencies, or outliers that could distort PCA results. To prepare the data, we first handle missing values, either by removing them or imputing reasonable estimates. Next, we normalize the features to ensure they are on the same scale. This is critical because PCA is sensitive to scale differences, meaning features with larger ranges can dominate the principal components and skew the results. Standardizing the data ensures that each feature contributes equally to the analysis. Once the data is clean and standardized, we move on to dimensionality reduction with PCA. Here, we compute the covariance matrix to understand how the features interact with each other. Then, we perform eigenvalue decomposition to extract the principal components and their corresponding eigenvalues. These eigenvalues tell us how much variance each component captures. The goal is to retain only the first few principal components that explain the majority of the variance, usually around 95%. This step significantly reduces the data's complexity while preserving its essential structure. With our reduced dimensional representation, we now move to reconstruction of data. PCA allows us to transform the data back into its original space by reversing the projection. This means we can compare the reconstructed data to the original data and measure how much information was lost. This is crucial for anomaly detection because anomalies often have higher reconstruction errors than normal data points. Since PCA captures the main structure of the data set, points that don't conform to this structure, outliers, tend to have significant reconstruction deviations. Now that we have our transformed data, we need to assign anomaly scores to determine which points are considered anomalies. The most common method is to calculate the reconstruction error for each data point. This error measures the difference between the original data and its reconstructed version from the principal components. If a data point has a significantly higher error than the rest, it likely deviates from the normal structure and is flagged as an anomaly. Another approach is using distance metrics, such as Mahalanobis distance, to measure how far each point is from the center of the transformed space. The farther a point is, the higher its anomaly score. The final step in the workflow is interpretation and action. Detecting anomalies is only useful if we can understand what they mean and take appropriate action. Once anomalies are identified, they need to be analyzed in the context of the problem domain. Visualization tools such as scatter plots of the first two principal components or histograms of reconstruction errors can help make sense of the results. From there, decisions can be made, whether it's flagging fraudulent transactions for review, investigating system failures, or identifying unusual patient health records that require medical attention. By following this structured workflow, PCA-based anomaly detection becomes an efficient and reliable method for identifying hidden patterns and outliers. But while PCA is powerful, it's not without its challenges. In the next section, we'll explore the key advantages of PCA-based anomaly detection, including how it simplifies data, reduces noise, and enhances interpretability. Let's keep going. Now that we've seen how PCA helps identify anomalies, let's talk about why it works so well. PCA isn't just another anomaly detection method. It has some unique strengths that make it a powerful tool, especially when dealing with high-dimensional and complex data sets. Whether you're working in finance, cybersecurity, healthcare, or manufacturing, PCA offers key benefits that make anomaly detection more efficient, accurate, and scalable. One of the biggest advantages of PCA is dimensionality reduction. Many real-world datasets contain dozens, hundreds, or even thousands of features, but not all of them provide meaningful information. Instead of analyzing all features separately, PCA condenses them into a smaller set of principal components that capture the most important patterns while discarding redundant information. This makes it much easier to spot trends, clusters, and outliers without getting lost in an overwhelming amount of data. Another major benefit is noise reduction. Raw datasets often contain irrelevant fluctuations or inconsistencies that can interfere with anomaly detection. PCA acts like a data filter, removing minor variations that don't contribute much to the overall structure. This leads to clearer signal detection, making anomalies stand out more distinctly. In machine learning applications, this can improve model performance by reducing overfitting and focusing only on the most informative aspects of the data. PCA also enhances interpretability, especially in high-dimensional data. When working with many features, it's often difficult to visualize relationships between variables. By transforming the dataset into a lower dimensional space, PCA makes it easier to understand the underlying patterns and identify anomalies that would otherwise be hidden. This is particularly useful for visual analysis, where anomalies can be plotted along the principal components for better insight. Another advantage is that PCA-based anomaly detection is computationally efficient. Unlike some other anomaly detection techniques that require intensive computations, PCA simplifies data in a way that reduces processing time. Since PCA extracts only the most important features, it allows anomaly detection to be performed faster, even on large data sets. This makes it an excellent choice for real-time or near real-time anomaly detection in industries like fraud detection, network security, and predictive maintenance. Finally, PCA is versatile. It can be applied to various types of data, including numerical, time series, and even image data. From spotting fraudulent credit card transactions to detecting failures in industrial sensors, PCA provides a generalized approach that works across multiple domains. Because it doesn't require labeled data, PCA is also useful in unsupervised anomaly detection, where anomalies need to be found without prior knowledge of what they look like. While PCA offers many advantages, it's not perfect. There are some challenges, such as sensitivity to outliers, difficulty handling nonlinear relationships, and the need to choose the right number of principal components. In the next section, we'll explore these challenges and discuss how to overcome them to make PCA-based anomaly detection even more effective. Let's keep going. While PCA is a powerful tool for anomaly detection, it's not without its challenges. Like any technique, it has limitations that need to be carefully managed to ensure accurate results. If used incorrectly, PCA can misinterpret patterns, overlook anomalies, or even introduce new biases. Let's break down the key challenges and why they matter. One of the biggest challenges is choosing the right number of principal components. PCA works by reducing the dimensionality of a dataset, but keeping too many or too few components can lead to problems. If too few are selected, important information might be lost, making it harder to detect anomalies. On the other hand, keeping too many can retain unnecessary noise, making the results less useful. A common approach is to use a scree plot to identify where the variance starts leveling off, but in complex datasets, this decision isn't always straightforward. Another issue is sensitivity to outliers. PCA is based on variance, meaning extreme outliers can heavily influence the principal components. If an outlier has a significantly larger magnitude than the rest of the data, PCA might align the components along that anomaly rather than the actual structure of the dataset. This can cause false negatives where anomalies get absorbed into the new principal components and go undetected. To mitigate this, robust preprocessing techniques such as removing extreme values or using robust PCA variants can help. Handling nonlinear data is another limitation. PCA assumes that relationships between features are linear, meaning it works best when data follows a straight line pattern in a high-dimensional space. However, in many real-world scenarios, like detecting fraudulent transactions or recognizing unusual behavior in sensor networks, relationships between features are nonlinear. Standard PCA struggles to capture these patterns, leading to suboptimal results. Nonlinear extensions like kernel PCA or autoencoders can sometimes help, but they add complexity. Another often overlooked challenge is data scaling and normalization. PCA relies on the assumption that all features contribute equally, but if some variables have much larger ranges than others, they can dominate the principal components. Features with higher numerical values may appear more significant just because of their scale, not because they contain more important information. Proper normalization and standardization, scaling all features to a similar range, is crucial for making PCA work correctly. Finally, interpretability of results can be difficult, especially in high-dimensional datasets. Since PCA transforms the original features into principal components, it's not always easy to trace anomalies back to specific, meaningful features. Unlike other anomaly detection methods that provide clear, human-readable insights, PCA-based anomaly detection often requires additional investigation to determine why an anomaly was flagged. This makes it harder for businesses and analysts to take action based solely on PCA output. Despite these challenges, PCA remains a valuable tool when applied carefully. Understanding these limitations allows us to improve its effectiveness by using proper data preprocessing, exploring robust variations of PCA, and combining it with other anomaly detection methods. In the next section, we'll compare PCA-based anomaly detection with other techniques and see when it's the best choice. Let's move forward. PCA is a powerful tool for anomaly detection, but it's not the only approach out there. Depending on the dataset, the type of anomalies, and the computational constraints, other methods might be more effective. So, how does PCA compare to other common anomaly detection techniques? Let's break it down. One popular alternative is isolation forest. Unlike PCA, which relies on variance and dimensionality reduction, isolation forest works by randomly partitioning the dataset into smaller subsets. The key idea is that anomalies are easier to isolate because they tend to stand out in fewer partitions. This method is robust to high-dimensional data, doesn't assume linear relationships, and is particularly useful when anomalies are scattered throughout the dataset. However, it requires a good balance of tree depth and sample size to avoid overfitting or missing subtle outliers. Another method is one-class SVM, support vector machine, which is commonly used for detecting anomalies in highly structured data. It works by learning the boundary of normal data and classifying anything outside that boundary as an anomaly. Unlike PCA, which assumes normal data follows a variance-based pattern, one-class SVM explicitly models normality, making it better suited for datasets where normal data points cluster tightly. However, it struggles with large datasets and requires careful tuning of hyperparameters. Autoencoders, a deep learning-based approach, offer another alternative. These neural networks learn to compress data into a lower dimensional space similar to PCA, and then reconstruct it. If the reconstruction error is high, the data point is flagged as an anomaly. Autoencoders outperform PCA when dealing with nonlinear relationships, as they can learn complex patterns beyond simple variance-based reductions. However, they require large amounts of training data and can be computationally expensive. K-means clustering is another simple but effective technique. By grouping data into clusters, K-means allows anomalies to be identified as points that do not belong to any well-defined cluster. It's a fast and interpretable method, but it assumes that normal data naturally forms clusters, which isn't always the case. So, when should you use PCA? PCA excels in situations where dimensionality reduction is a key concern and where anomalies can be identified based on how much they deviate from principal components. It's particularly useful in pre-processing steps, helping other anomaly detection methods perform better by reducing noise and redundancy. However, for nonlinear data, highly structured datasets, or cases requiring explicit decision boundaries, methods like isolation forest, one-class SVM, or autoencoders might be a better choice. Each method has its strengths and weaknesses, and in many cases, combining PCA with other techniques leads to the best results. Next, let's see PCA in action with real-world case studies, starting with anomaly detection in network security. Let's dive in. Cyber threats are becoming more sophisticated every day, and traditional rule-based security systems often fail to catch subtle anomalies that indicate a potential attack. This is where PCA-based anomaly detection proves to be a game changer. In network security, anomalies often manifest as unusual traffic patterns, unauthorized access attempts, or sudden spikes in data usage. By leveraging PCA, security teams can detect these anomalies in real time, helping to prevent cyber attacks before they escalate. In this case study, PCA was applied to analyze network traffic over a 6-month period. The dataset contained 1.5 terabytes of network activity logs, including details on data packets, connection durations, and IP behavior. Traditional methods struggled with the sheer volume and complexity of the data, making it difficult to pinpoint abnormal activity. PCA was used to reduce the dimensionality while retaining the most informative features, allowing security analysts to focus on deviations from the normal traffic pattern. After pre-processing and standardizing the data, PCA was applied to identify principal components that captured 95% of the variance in normal network behavior. The next step was to measure anomaly scores based on reconstruction errors, a technique that flags data points that deviate significantly from the expected structure. Using this approach, 150 unique anomalies were detected, including suspicious data transfers, unauthorized remote logins, and potential malware activity. The impact of this approach was significant. The PCA-based model achieved a precision rate of 92% and a recall rate of 85%, meaning it successfully detected most real threats while minimizing false positives. Additionally, the average response time to security incidents was reduced from 48 hours to just 12 hours, allowing IT teams to act faster and mitigate risks before major damage occurred. One of the key advantages of using PCA in network security is its ability to handle high-dimensional data efficiently. Traditional anomaly detection methods often struggle with massive datasets, but PCA makes it possible to extract meaningful insights while maintaining speed and accuracy. However, one challenge was ensuring that PCA captured dynamic changes in network behavior over time. To address this, the model was updated periodically with new training data, allowing it to adapt to evolving threats. This case study highlights how PCA can play a crucial role in cybersecurity, helping organizations proactively detect and respond to threats. But network security isn't the only field where PCA-based anomaly detection proves valuable. In the next case study, we'll explore how it's being used in healthcare to identify medical anomalies and improve patient outcomes. Let's continue. In healthcare, detecting anomalies isn't just about identifying data outliers. It can mean the difference between life and death. Medical anomalies such as irregular vital signs, abnormal lab results, or unusual patient symptoms can indicate underlying conditions that require immediate attention. However, with massive amounts of patient data being generated daily, traditional detection methods often struggle to identify subtle but critical deviations. This is where PCA-based anomaly detection comes in, offering a data-driven approach to uncover hidden medical insights and improve patient care. This case study focused on using PCA to analyze patient health records from a hospital system over a 1-year period. The dataset contained thousands of features, including heart rate, blood pressure, glucose levels, oxygen saturation, and lab test results. While most patient records followed expected patterns, some contained subtle irregularities that might have been overlooked by traditional rule-based systems. By applying PCA, the dataset was transformed into a lower dimensional space, making it easier to spot outliers that deviated significantly from normal physiological trends. After pre-processing and normalizing the data, PCA was applied to extract the most informative principal components, reducing the dataset while retaining over 95% of the variance. Once the data was projected onto these components, distance-based anomaly scoring such as Mahalanobis distance was used to flag patient records that deviated beyond the expected range. The results were compelling. PCA identified 15% of patient records as potentially anomalous, leading to the discovery of previously undiagnosed conditions such as early-stage diabetes, cardiac irregularities, and oxygen deficiencies. The impact of PCA-based anomaly detection in this case was profound. Doctors were able to intervene earlier for patients showing warning signs of serious conditions, reducing hospitalization rates and improving long-term treatment outcomes. Additionally, the system helped optimize hospital resource allocation by prioritizing high-risk patients, ensuring that medical staff could focus on the most urgent cases. One of the challenges encountered was interpreting the principal components in a clinical setting. Since PCA transforms data into a new coordinate system, it was sometimes difficult for doctors to directly trace an anomaly back to a specific medical variable. To address this, hybrid models were used, combining PCA with explainable AI techniques to improve interpretability. Another consideration was the dynamic nature of patient data. To keep the anomaly detection model up to date, the PCA model was periodically retrained with new patient records, ensuring it adapted to changing medical patterns. This case study demonstrates how PCA can significantly enhance patient monitoring and early diagnosis, leading to better medical decision-making. But the healthcare industry isn't the only place where PCA-based anomaly detection is making an impact. In the next case study, we'll explore how it's being used in finance to detect fraudulent transactions and prevent financial crime. Let's continue. Fraud is a multi-billion-dollar problem in the financial sector, with criminals constantly developing new ways to manipulate transactions and exploit vulnerabilities. Traditional fraud detection systems often rely on rule-based models, but these can struggle with evolving fraud patterns and generate high numbers of false positives, frustrating both customers and analysts. PCA-based anomaly detection offers a more adaptive approach, identifying suspicious financial transactions based on hidden patterns rather than predefined rules. In this case study, PCA was used to detect fraudulent transactions in a dataset containing over 1 million banking transactions from a major financial institution. Each transaction had multiple features, including transaction amount, location, time, frequency, and account activity history. The challenge was that fraudulent transactions were rare, less than 0.25% of the dataset, making traditional supervised learning methods less effective due to an extreme imbalance between normal and fraudulent cases. To address this, PCA was applied to reduce the dataset's dimensionality while preserving key variance. After standardizing the data, PCA extracted the most relevant principal components, capturing over 95% of normal transaction patterns. The next step was to compute anomaly scores based on reconstruction errors and distance metrics. Transactions that deviated significantly from the principal component space, such as sudden large withdrawals from dormant accounts or transactions in unexpected locations, were flagged for review. The results were impressive. PCA-based anomaly detection identified 2,500 high-risk transactions, leading to a 30% reduction in false positives compared to traditional fraud detection models. This meant fewer legitimate transactions were mistakenly blocked, improving customer experience while still catching fraudulent activity. Additionally, fraud investigators were able to focus on truly suspicious cases, reducing investigation time and enhancing operational efficiency. One of the main challenges was real-time processing. Since banking transactions occur continuously, fraud detection needs to happen within milliseconds. To make PCA suitable for real-time applications, incremental PCA was used, allowing the model to update dynamically as new transactions were processed. Another challenge was explaining flagged anomalies to analysts. Since PCA transforms the original features, investigators needed additional tools to understand why a transaction was considered suspicious. To improve interpretability, PCA was combined with other machine learning techniques, such as decision trees, which provided human-readable insights alongside PCA scores. This case study highlights how PCA can be a powerful tool for financial anomaly detection, improving fraud detection accuracy while reducing customer friction. But how do we know that PCA is actually performing well? In the next section, we'll explore the key performance metrics used to evaluate PCA-based anomaly detection and ensure that it delivers reliable results. Let's keep going. Detecting anomalies is one thing, but how do we measure whether our PCA-based method is actually doing a good job? In anomaly detection, accuracy alone isn't enough because anomalies are rare. Even a model that classifies everything as normal might appear to be performing well while missing the most critical cases. To truly evaluate PCA-based anomaly detection, we need to look at a combination of precision, recall, and error analysis to ensure we're flagging the right anomalies without overwhelming the system with false positives. One of the most important metrics is precision, which tells us how many of the flagged anomalies are actually real anomalies. A high precision score means fewer false positives, critical in areas like fraud detection, where mistakenly blocking legitimate transactions can frustrate customers. However, focusing only on precision can lead to missing subtle anomalies, so we also need to consider recall, which measures how many actual anomalies were successfully detected. A low recall score means the model is missing important cases, which could be dangerous in applications like cybersecurity or healthcare. To strike the right balance, we use the F1 score, which is the harmonic mean of precision and recall. A high F1 score indicates that the model is both accurate and comprehensive, catching real anomalies while minimizing false alerts. Another essential evaluation tool is the ROC, Receiver Operating Characteristic curve, which plots the true positive rate against the false positive rate at different thresholds. The area under this curve, AUC score, provides a single number to summarize how well the model distinguishes between normal and anomalous data. But evaluating PCA-based anomaly detection isn't just about precision and recall. It's also about understanding how anomalies are scored and classified. One approach is to analyze reconstruction errors. By looking at the difference between the original and PCA reconstructed data, we can determine if our method is capturing meaningful deviations. If anomalies consistently show higher reconstruction errors while normal data stays close to zero, we know PCA is working effectively. Another technique is using a confusion matrix, which provides a detailed breakdown of how many true positives, false negatives, and true negatives the model produces. This allows us to fine-tune the PCA model, adjusting the number of retained principal components or tweaking anomaly thresholds to optimize performance. To ensure reliability, many organizations also implement cross-validation techniques, such as k-fold cross-validation, which helps assess the model's stability by testing it on different subsets of the data. This prevents overfitting and ensures the anomaly detection system performs well on unseen data. Ultimately, the goal of evaluating PCA-based anomaly detection isn't just about getting a good score, it's about making sure real-world anomalies are detected early and accurately. With strong evaluation methods in place, PCA can be trusted as a valuable tool for identifying hidden patterns in large data sets. But what does the future hold? In the next section, we'll explore emerging trends in PCA-based anomaly detection and how it's evolving with deep learning, real-time analysis, and AI-powered insights. Let's move forward. Anomaly detection is evolving rapidly, and while PCA has been a powerful tool for dimensionality reduction and outlier detection, the future is bringing even more advanced techniques. As datasets grow larger, more complex, and more dynamic, PCA-based anomaly detection is being enhanced with deep learning, real-time processing, and hybrid models to improve accuracy, interpretability, and speed. One major trend is integration with deep learning. Traditional PCA is a linear technique, meaning it struggles with nonlinear relationships in high-dimensional data. However, by combining PCA with autoencoders, a type of neural network, we can learn more complex feature representations while still leveraging PCA's ability to filter out noise. Autoencoders work similarly to PCA but are more flexible, making them better at capturing intricate anomaly patterns in financial fraud, cybersecurity, and medical diagnostics. Another exciting development is real-time anomaly detection. Many industries, such as finance, network security, and industrial monitoring, require anomalies to be detected within milliseconds to prevent fraud, cyber attacks, or equipment failures. Traditional PCA can be slow when applied to massive datasets, but advancements in incremental PCA and streaming PCA allow models to update dynamically as new data arrives. This ensures that anomaly detection systems remain adaptive and responsive without needing constant retraining. Explainability and interpretability are also becoming a major focus. One challenge with PCA is that its transformed components don't always map directly to human understandable features. Future solutions involve hybrid models that combine PCA with explainable AI techniques such as Shapley additive explanations, or LIME, local interpretable model agnostic explanations. This makes it easier for analysts to understand why a transaction, network activity, or medical record was flagged as anomalous. Another trend is adaptive thresholding, where anomaly detection models adjust their sensitivity based on historical data and changing trends. Instead of using fixed distance metrics to define anomalies, models are now incorporating probabilistic methods and Bayesian inference to dynamically adjust thresholds, reducing false positives while still catching important anomalies. Lastly, hybrid approaches are gaining popularity. Instead of relying on PCA alone, organizations are combining it with other anomaly detection methods, such as isolation forest, one-class SVMs, and deep learning models. These multi-layered approaches allow PCA to handle dimensionality reduction and noise filtering, while other algorithms focus on nonlinear relationships and decision boundaries. This creates more robust anomaly detection pipelines that can handle a wider variety of datasets and anomaly types. As anomaly detection continues to evolve, PCA remains a key foundation, but is now being enhanced with AI, automation, and real-time analytics to meet the growing challenges of big data. In the next and final section, we'll wrap everything up with a summary of key takeaways and the future role of PCA-based anomaly detection. Let's bring it all together. We've covered a lot in this deep dive into PCA-based anomaly detection, from its mathematical foundation to real-world applications in cybersecurity, healthcare, and finance. Now, let's bring it all together with the key takeaways and a look at what's next. Principal component analysis, PCA, is a powerful dimensionality reduction technique that helps in filtering out noise, simplifying complex data sets, and making anomalies more detectable. By projecting data onto a lower dimensional space while preserving key variance, PCA allows us to spot deviations that wouldn't be obvious in raw data. This makes it especially useful in high-dimensional datasets where traditional anomaly detection methods struggle. We explored the step-by-step workflow of PCA-based anomaly detection, from data standardization to computing principal components and scoring anomalies based on reconstruction errors or distance metrics. While PCA alone can effectively uncover hidden patterns, it works even better when combined with other methods such as distance-based scoring, isolation forest, or deep learning techniques. We also examined real-world case studies that demonstrated PCA's versatility. In network security, PCA was used to detect unusual traffic behavior, preventing cyber attacks before they escalated. In healthcare, PCA helped identify medical anomalies, leading to earlier diagnoses and better patient care. In finance, PCA improved fraud detection, reducing false positives while catching suspicious transactions. Despite its strengths, PCA has challenges. It assumes linear relationships, is sensitive to outliers, and can sometimes be difficult to interpret in practical applications. However, new advancements such as hybrid models, real-time adaptive PCA, and deep learning integrations are addressing these limitations, making PCA even more effective. Looking ahead, PCA is evolving with AI-driven anomaly detection, real-time processing, and enhanced interpretability tools. By combining PCA with advanced machine learning techniques, organizations can create more accurate, scalable, and efficient anomaly detection systems. So, what's the big takeaway? PCA is more than just a mathematical trick. It's a fundamental tool for making sense of complex data, uncovering hidden risks, and driving smarter decision-making. Whether you're detecting fraud, securing networks, or improving healthcare diagnostics, PCA continues to be a critical technique in modern anomaly detection. And that wraps up our session. If you found this valuable, make sure to explore how PCA and other anomaly detection techniques can be applied to your own datasets. Thanks for joining, and let's keep pushing the boundaries of data science.